Okay, guys, we're doing the first section of first part of 3 parts of Review 7, which is the review problems for the third exam. Okay, so let's look at this problem here. Today we're going to do just the 3 problems in statically indeterminate torque-loaded members. And you will remember that we did statically indeterminate axially loaded members, and it's very similar, okay? The first thing we remember is to remember what is the order of work. How do we solve these statically indeterminate problems where you have this shaft, for example, that is stuck in the wall, basically fixed at both ends, and it has some sort of load in the middle, and it also has 2 different cross sections. So the way to do this problem is, you see the dimensions. I'm not going to read them, but the point is that we have 3 different sections. The first section is a small radius, no loads. Then the radius changes, so that's the second section, up to a torque. And so that's where we have a new section, same radius, but it's on the right-hand side of the torque. So 3 sections. And the first thing we need to do is to write down the equilibrium condition. Okay, so first is equilibrium. And it really comes from the sum of all torques is equal to 0, right, for this member. And we will know what they are when I actually draw a free body diagram. And I'm going to do it like this. I'm going to draw a thick part, oh, it's getting thicker and thicker. Okay. Looks funny, but it works. I'm going to use a thinner pen. I don't like these thick pens, okay? And so I'm going to draw, to sketch, right? Because we don't know yet anything about this. I'm going to sketch a free body torque distribution, but not before I draw the torques, right? So what do we have? We only know that we have this torque here. Maybe I should use a different pen, a little darker. And that's a 500 pound-foot. And when we remove the walls, now we will have the torques in the opposite direction from this one, because it's the only one we have. So we're pretty sure that they're going to be in this direction, TA and TB, but we don't know what they are. So that's our free body diagram. And from there, we can look at our equilibrium condition, write down the equilibrium condition, which says that sum of torques is 0, from which it follows that TA plus TB minus 500 is equal to 0, and I'll just write it as equal to 500. And so we see that these two guys, since we are sure about the sign, that we know they're going to be both smaller than 500. Are they going to be 250 each or something different? We don't know yet, but we're confident about this. So about this time, we could actually just draw the distribution of torques, which we will need for our equations, okay? And I'm going to use a red for this. And so I'm going like this. I'm going up, okay, by a certain amount. And then in going to the next section, which is change of diameter. Is there a change in torque? No. So it remains, this is TA. And I'm going to go with 2 arrows indicating sort of that's a colloquial way that I've just decided to use of saying that it's a torque, not a force. but to indicate some sort of direction. And so there's no change at this change of cross section. There's no change of torque. Other things will change, but not torque. And so it stays constant all the way up till this point here. Okay, so we have all these different points. This is A, this is a C, a D, and a B. At D, it suddenly, the torque changes in the opposite direction and becomes 500. Now notice that this torque, the TB, has to be the same sign as TA, but it has to end at 0, right? And so I know that it should be going this way. So I know that this amount here, whatever those two amounts are, we don't know, but we know that this amount should be 500. Okay, and this is TB. And so now we have our diagram. And this is important because you want to be able to always, at each of these three sections, know what the torque is. That's the key point. Okay, so let's now go to the next step. The next step is to write the load displacement equation. And it's simple. It's not one equation. There are many, but I'm going to write the generic form for torque. And then we're going to be using it in our compatibility equations that come, a compatibility condition that comes right after. It would look something like this. The angle of twist. So in torque, the load displacement equation connects the angle of twist and the torque that caused it. Okay, so the angle of twist typically is going to be equal to T as a torque times L, the length of the section, over J, the moment, polar moment of inertia of that cross section, times G, the shear modulus of this material. Okay, so we have all this information. Well, so now let's write the equilibrium equations. I'm sorry, not the equilibrium equations, but compatibility condition. Okay, so what's the compatibility condition for this case? The compatibility condition is this. Where is the only load? Right here. We know that it has to be the angle of twist is 0 at both ends because it's pinned. So if you're going from right to left, the angle of twist will be changing. It will be growing. If you're going from left to right, the angle of twist will be changing. Right at this point, those two angles we just talked about have to become the same because there is no sharp changes in the angle of twist at the sample. If that happens, that means it just broke, okay, a split second after breaking. So that's not the case we're studying in this course. So the compatibility condition says that the angle of twist from D with respect to B has to be equal to angle of twist of D with respect to A. So let's write that out. Let's go step by step. So I'm writing first D with respect to B. That's just this section right here, and this is the load, and this is how we find the internal torque that we need for this. And so let's write it out. Internal torque in this case is just TB, okay, times L is 12 inches, right? I forgot to say the lengths here. So this is 5, this is 8, and this is 12. Okay, and so it will be TB times, and we are going to remember that we are dealing with feet and inches, okay? And so at some point we will have to change that into feet and inches, okay? We have to recognize one thing. In these two equations, what will be changing? T, L, and J. The only thing that will not be changing is G. So it doesn't even matter we were given this. For this particular step, it doesn't matter that we were given the shear modulus because we are not going to use it. So I'm not even going to substitute the value. Open your eyes to that and use it in every problem. It will just cancel out. So TB times 12 over, And now we have to calculate the two J's. The J for this guy here, so I'll call that JAC, is equal to pi over 2, and then the radius to the fourth power. The diameter is 0.5, so the radius is 0.25 to the fourth power. And this is in inches. And here, in this section, JBD, well, actually, JC from here to there, CB, that entire span is equal to pi over 2, and then half of this diameter, which is 0.5 to the fourth. And so we need to remember which one we are using. In this case, for D to B, we're using this one. So it's pi over 2, 0.5 to the fourth times G. And that's it. There's nothing else from D to B. It's just that one. But now we need to calculate this one. And that's going to be a little harder. This one's going to be a little harder because we have first that cross-section and then the other cross-section. But as we see here, for both of these, the torque is the same. The cross-section is different. So we just add them up. So what's the first one going from D to C? The torque is TA times the length is 8 divided by the J there, this is still the big J, so that's a pi over 2, 0.5 to the fourth power times G, okay, and then plus this bit here, but the T is the same there, it's again TA, but now the length is 5 inches. Okay, the length is 5 inches, and the J is this J here, so that's the little j, so it's pi over 2, 0.25 to the fourth. Okay, and so when you sort this out, you will get these numbers. You will get 1408 TA is equal to 192 TB. And so now I'm going to use, let me see which pen, maybe I will use an orange pen to highlight when you solve this equation and that equation. Two equations, two unknowns, you get what? You get that TA is equal to 60 pound-foot and that TB is equal to 440 pound-foot. So notice that here we don't have to worry about inches and pounds, inches and feet, because we use both L and the diameter in inches. So it all cancels out in inches, okay? So there's inch here and inch there, and you get inch to the third remaining at the bottom. And so inch to the third gets canceled on both sides. So it doesn't matter, as long as you stick to one dimension, through both on top and the bottom, both in the numerator and denominator, you're fine. This equation is valid, okay? What numbers you got are the same whether you had it in all feet or all inches, but not here foot and here an inch. It's not acceptable. So these are your T's. And so now you know the T's, okay? You can calculate the maximum shear stress, okay? Because we're supposed to find, determine the maximum shear stress in the shaft. Now, will you just go straight for the torque? Because you know shear stress is proportional to the torque. Well, no, you won't, because yes, this torque is bigger, but it's acting on this side with a larger cross section. So we need to determine, it will depend on both on the cross section and on the torque. So let's write it up. Let's write up the last part of the problem, which is the shear stress. The shear stress for the section AC, we'll call it tau AC. And it goes without saying that we're talking about the maximum shear stress, right, at this point, because we're looking at the biggest values in that section. For the AC, the value will be TA, right, times let's write what the shear stress is here. T times C, which is the maximum diameter, over, maximum radius, over J. Okay, so our C is half of the diameter, which is 0.25. Okay, and there we got to make sure that we multiply with feet here. Okay, so I will undo this and multiply here with 12. 12 goes for 12 inches in a foot because the TA is in pound foot. So instead of foot, I'll write 12 inches. So now everything is in inches. Times the length, the C, the radius of that section is 0.25. And below we have the JAC, which is pi half 0.25 to the fourth. And when you calculate that, these two cancel, obviously, and that's a third. And so when you calculate that, you get that the tau AC is 29.3 KSI, kilopounds per square inch, okay, when you sort out the units, because the TA is 60 pound foot. Next, we calculate for the section BC, that's the one that includes that radius. So it will be, we have to stop here and think. So when you look at, now we know that this amount here is 60. So this one is actually bigger than that one. And this amount here is 440. So this is kind of around here. So clearly for the fat section of the shaft, this amount here is bigger than that amount there, okay? And so if you really want, I can correct it a little and draw this bigger so that it makes sense, so that it's obvious to what we are doing. Oops, that's not much bigger. That makes sense. And so that's 440. So now this is much, much bigger, okay? So that section has the maximum torque, and it's the same diameter. So we know that the maximum torque in that section will be here, and it will be 440, and it's the same diameter. So the tau at the whole section CB is equal to the tau at this section. That's the maximum shear stress at the section DB. And that's equal to T, the torque B, because that's the amount, 440. And you know, I don't even want to confuse you. I really want to just put in directly the value, because we're not looking at the torque, and that goes the same here. I'm going to write down the number, okay? The numbers are, because we're looking at the number, not at the torque. These are the numbers. So this is 60 here because we're looking at this amount, okay, that amount. And here we're looking at this amount. So that amount is 440 times C, and that's half of this diameter, which is 0.5. But let's not forget the 12 for the inches and feet. So it's 0.5. And down at the bottom, we have pi over 2, 0.5 to the 4th power. This and that gets canceled. This is a 3rd power. And the final solution is 26.9 KSI. And so we're asked to determine the maximum shear stress in the shaft. So which one is the maximum shear stress in the shaft? It's this one here. Which sort of we could have guessed because it's the thinnest, but still it doesn't necessarily mean, because the torque, it's the ratio of the torque with the 3rd power of the diameter. So that's hard to guess. So that one's slightly bigger than this one. So the maximum shear stress in the shaft is in this cross section. Okay, that's the end of that problem. Now we have a different problem where we have two shafts that are not collinear. They're slightly apart because one is running one gear. It's basically two gears touching, and the torque is transmitted from one to the other. So there you have to think hard and remember what are really, this is just common sense, but also mechanics. The condition of compatibility will be slightly different from what we did in the previous problem, but it's all logical, okay? So we have the steel, they're the same diameter. The gear diameters are different, but the shaft diameters are the same. There is a torque on the lower one of 500 Newton meters, and the distance to the wall of the little one is 0.75 and of the big one is 0.15. So we have two walls, we got to get rid of them, okay? And so we're going to start solving the problem one by one, okay? First thing I would do here is to write the equilibrium equations, but for what? Since we have two bodies and they're moving with respect to each other, each is stuck in the wall, we really, unlike the previous problem, we have two free body diagrams that we need to draw, okay? So the first, and I'm going to draw them in line. So the left one looks like this, and it has a big gear here, and it's removed from supports there, okay? And the other one, I'm going to separate it a little sideways. It's shorter, also separated from the wall, has a smaller gear, okay? And so what are the loads on them? Let's sort that out. On this one, we have a torque like this, TA, we'll call that TA, and that's a point A. Okay, this is a point E, and that's a point F. And now, in point E, what we have is the following. When we separated these two, we both have the torque. We have the torque, right, on the bottom one. But we also have the force on both of them. Okay, and I'm just going to draw how it looks when I separate them. Like this. This is the big and this is the little guy. And it looks like this. This one, the force due to the little one is right here. And then this one has the same, only in opposite direction, because that's how the free body diagrams work. When you throw one away, you put in a force, and then that's the same force that accounts for the missing of that one when you're drawing the other one. Okay, so it's the same but opposite direction, and I'll call it F. And so here we will have a torque like this, opposite from this, right? And there will be a force there too that is, yeah, I guess I didn't really draw this properly. I should have, I'm going to erase it, and I should do it in isometry because it's easier to look. So let me erase all this and do it the same way they did it. Sorry about that. Okay, so this one looks like this, and it has that. And so the force is here. Oops. That's the force, right? The torque on this end is in this direction. That's the end A. And so this is TA. And the torque here is in this direction. And that's 500 Newton meters in this case. And this is an F. And this distance here is 0.5 meters. So I'm going to use a different pen and say this guy here is 0.5 meters. Then we want to look at this guy, the little guy. And so the little guy looks kind of the same, like this. And the force is in the same, on the same place. I'm going to erase the other one. Same direction and same line and magnitude, but different direction. Okay. And I'm really not going to use this either because I don't like it. But I will indicate the radii with the green. And so this one has a radius that's very small, right? Like that. So this radius is 50 millimeters. So it's 0.05. And this radius here is 0.1. And this is a force, the same force as this one. So now we have everything, but this one doesn't have a torque. It only has it at this end here, and it would be going in that direction, right? Because this is pushing it this way, so this is resisting that way. And that's a TB. And so now we have everything. These are the pictures. And let's look at here the radii and what they will give us. And here this little one, okay? Because we'll need that when we're calculating the equilibrium. So now we have everything. So let's write the equilibrium equations. And maybe I can, for a change, use a violet. Okay, so equilibrium. Let's look at this one first. So we're going to have two equations, one for this body and one for that body. Okay, and then after that, we're going to write some sort of compatibility equation. So sum of torques is 0 for this section. Not for this section, for this free body diagram. TA, so I'll decide that that's a positive. And then F will be in the same direction, so it's going to be plus F times 0.1, because this force will create a torque around that axis, right? And then minus 500 is 0. So that's the first equation of equilibrium. And another equation of equilibrium, we don't know what this F is. It's some sort of reaction, okay? The only thing we know is that these two F's are the same. The other equation of equilibrium for this body would be, so I'm now going to choose that this is a positive direction. so it's TB. And then the only other thing that we have is the opposing guy, this F. So it's going to be minus F times what? 0.5, 0.05 is equal to 0. Okay? And so when you put these two equations together, you substitute F because F is the unknown, right? Calculate F from one or the other, you get that they come to be this. TA plus 2TB is equal to 500. So that's my equilibrium. That's what we could squeeze out of equilibrium. Now let's go and start writing up the compatibility equation, because we know that it involves the angle of twist, and we know that angle of twist is usually internal torque at that location times the length of that section times the polar moment of inertia divided by polar moment of inertia and the shear modulus G. So remember the formula. So I don't need to write that load displacement formula over and over again. But let's see the compatibility. Condition. The compatibility condition in this case, remember before we said that the twist angles, we just had a single shaft, and then the twist angle at any point, from that point to the left and from that point to the right, those two twist angles have to be the same. But here, we don't have the twist angles really because they're not along the same axis. There is a shift. And so what you see is that we know that these two forces have to be the same, these two F's, right? So really, if you look at what happens, let's say, at the particular twist location. So we are having a big wheel, that's this one, that one, and let's say we're looking at this point here, and I'm going to call that point K. And let's see, originally it was there, and after I twisted it by some amount, it came to here. That's the same amount that because they're gears, the little gear is, the perimeter of little gear is traveling by this same amount, okay? And so what we need to equate, we are not equating the angle really, we're equating this length, because when you have a smaller circle, that length is going to be the same, but the angle, so this is for the smaller circle, right? The angle will be much bigger. So in this case, the compatibility doesn't talk about the angles of this big circle and the little circle. It talks about the path. And so how do we calculate the path of what's this arc equal to? If we have an angle phi and a radius r. The length of this is equal to, and I'm going to call it a cursive L. That length is equal to r times theta. I'm sorry, phi. Okay? And so now that you know that our compatibility condition will actually be that these two arcs are the same, the arc for the big wheel, gear, and the arc for the small gear are the same. So let's write it up. What is the arc of the big angle when the angle of twist changes? So that's the angle of twist at this point. At this point is 0, at that point is E. So what do we say? That's the angle of twist from E to A. That angle of twist times the radius of the big guy, which is 0.5. And that should be equal to that same arc length, but on the little gear, which is equal to the angle of twist of this shaft, which is from F with respect to B. Oops. Times the radius of the little guy, which is half of 50, which is 0.25. Okay, and all we have to do is now write these two radii. Okay, so these two twist angles. So what's the twist angle of this guy with respect to there? So it's basically from here to there. There's nothing, no changes in cross section, no new loads. So we know that internal torque here is 500. Okay, we know that internal torque is not 500, I'm sorry. It is, when we draw a diagram for the torque, it will start from TA and it will go constant until here, where it becomes changes. We have a 500, but we also have F times 0.01, just like what we wrote here. Okay, so this is the equation that guides that. And so it's really just TA. It's just the torque across this whole length is TA, and the torque across this whole length here is TB. So let's just write it up. So for the first one, we write TA times the length is 1.5 over JG. Why am I not substituting anything here? Because it doesn't matter. These two shafts have the same diameter, so those things are going to cancel, and they're made of the same material. But when they're not, I would have to substitute. But because I know they are, I'm just keeping it like that, and they will cancel. And that's equal to what? I'm sorry, that's times 0.5, and that's equal to this guy, which is again TB times, and now this length is 0.75 divided by JG times 0.25. And so JG's cancel, and this all gets sorted out, and you get the TA is equal to 0.25 TB. And so now what you have is you have those two equations. You have this one too, and that one there. And when you solve the system of two equations with two unknowns, you get the TA is equal to 222 Newton meters, go figure, and TB is equal to 55.6 Newton meters. And these are our solutions. Okay, these are the reactions in the supports.